Hello. In the last lecture, I have started chapter 7. Chapter 7 is about the sampling distribution. Let me start. So at the beginning of this chapter, what I want to emphasize is two simple things. You have to understand what is random. You have to understand what is random and think about what we can do if something is random. So these two are very basic starting points of this chapter. First, when we say something is random, then it's what a randomness means. So if you repeat an experiment, if the outcome can be different, then the outcome is random, right? So that's obvious. And also, when something is random, you know that we can define its probability distribution. So when something is random, there must be some probability for that. And also, you can calculate the mean and the variance as long as the outcome is a number, right? So it is easy to understand these two basic, very basic statements. Then now, keep these two statements in mind. What I'm going to do here is I will totally change the concept of experiment. Now, an experiment is now a survey. So think about surveying 1,000 people and ask their annual income, and then the outcome from that survey is the average annual income. So there is no difference in the structure. The experiment is it's surveying 1,000 people, and the outcome is the average annual income from 1,000 people, and the outcome is random because if you do the survey again, then the average income you calculate would be different because you will encounter different set of 1,000 people. So the average would be different, right? So we can think of like X bar, we define the average from a finite number of observations as X bar, and it is random. That's what you can find intuitively, right? Pretty intuitive if you understand survey as one experiment. So this is the point. Now, experiment is not just one experiment, but it can be a collection of multiple experiments. So it's an extension of your thought. And then because it is random, then what you can do now is we can study its probability distribution and we can study its mean and its variance. That's what we're going to do in this chapter. And to begin, the experiment we consider here is the random sampling. So survey is just it's a one example of random sampling. So in statistics, we call this kind of experiment as a random sampling. It means you are collecting a number of observations, and it can be a lot, but anyhow, there are n. So we usually denote n like for the size of the random sample. So the size of the random sample is usually denoted as n, and then in one random sampling, which is one experiment, in one random sampling, you observe n number of observations, which becomes one outcome. Because in one experiment, you are kind of think like this, not just throwing one coin, but you throw like 100 coins at the same time, 100 dice at the same time. So like that, you are observing a lot of things at the same time, right? That's what we will have in mind in our statistical inference later, because survey so you observe a number of observations. Then what we want to study here is if you recollect the data or regenerate the data, so if you recollect the data, would your can you replicate your conclusion or not? So we will imagine I do my own analysis based on say 1,000 people, but there may be another researcher who does the same thing, who analyzes the same thing, but from different set of data. Then what would be the difference? What would be the probability distribution of our results, for example? That's what we're going to do. So in the previous chapters, so the key distinction from the previous chapters is that one experiment is not actually one experiment in here. In this chapter, from now on, one experiment is observing a lot of observations, observing data, right? It is called random sampling. So I forgot to mention this. There are two assumptions for random sampling, and it's kind of very fundamental assumptions, but also they are theoretical assumptions, and they are required. So I am going to assume these assumptions are satisfied like all the time from now on. So I'm not going to question these assumptions in this course. So in this course, these assumptions are automatically satisfied when I say you have a random sample, or when I say you have data, when you have sample, you have observations. Like implicitly, I'm assuming that the data observations satisfy those two basic conditions, which is not a big deal. Like later, if you study further, then these assumptions become critical and should be investigated, but now I'm not going to touch them. So anyhow, we are going to study the basic ultimate goal of this chapter is to learn about the distribution of X bar, which is the average of many observations, average of the random sample. That's what we are going to do in this chapter. So later, just a spoiler, we are going to study the mean and the variance of X bar. It's much easier than you may imagine. And we are going to study the probability distribution of X bar. Another spoiler, the answer is normal distribution. That's the power of normal distribution. So no matter what X is, X bar, no matter how you collect the data, as long as the two assumptions are satisfied, X bar follows a normal distribution. That's why we can use the normal distribution for any single example in this course. Okay, then another thing I'd like to mention here is that it's very confusing, because usually, like in your mind, you may think mean equals average equals expectation. That is right, but can you think about mean of mean, average of average? You can think about that. So say X bar is a sample mean, which is the average calculated from say 1,000 people, right? It's natural to understand, but I said it is random. You agreed. It's easy to accept that, easy to imagine that it is random, because if you resample the survey respondents, then you will get different outcome. So it's random. So it has probability distribution. So it has its own expectation, which will be denoted this way. So X bar itself is a random variable. So it has its own mean. Any random variable has a mean. So sample mean has a mean. That is the mean of a sample mean, right? So the meaning of mean, and these two mean, the first mean is the population mean, which is the true mean if you observe the infinite number of observations. But the second mean is a sample mean, as you can see here. So this mean is calculated from the finite number of observations. So when you think about mean, you have to tell if it is from the sample or the population. More simply speaking, roughly speaking, the sample mean is calculated from a finite number of observations, so it is random. However, the population mean is calculated from an infinite number of observations, which is unknown. You cannot get there, but it's theoretically just hypothetical and theoretical object. But that is the true mean, right? So these two, the distinction between the sample and the population is really important from now on, because like that determines which is random and what's not. So so from now on, to reduce confusion, I will call the sample mean as the average, more casually, and I will use expectation instead of the population mean. So this is just simple rule. I may break the rule sometimes, but when there can be a confusion, I will try to distinguish them this way, or I will explicitly tell you it is sample or it is population. So the distinction between sample and population has been discussed from chapter 1, so it will become more important in the following chapters in statistical inference. So make sure what we are talking about, what you are handling. So now let's think about, okay, now we will consider the simplest possible example. The main theme of this chapter is that one experiment has multiple observations. That's the point. So the simplest possible example is this: throwing two dice at the same time. So you throw two dice. So that throwing two dice is one experiment. And then you observe two outcomes, and we calculate their average. We calculate the average outcome from those two dice. And you know, it is really simple, fair dice, and everything is well known. So try to calculate this. What is the probability that the average from this experiment, throwing two dice, what is the probability that the outcome, the average dice number, is 6? Calculate this probability, and it's simple, and I will continue in the next video. So watch the next one after you find trying this question. See you in the next one.